Hello, hi, I'm John Michael Hand, Senior Director of Product Planning at FADU, and I'm going to give you a presentation about flexible data placement that I gave at the Flash Memory Summit this year in Santa Clara. I did a very fun experiment about multiple namespaces and flexible data placement, and I was on a broader panel, but I'm going to give kind of an extended version that goes a little bit more in depth about FTP. So you'll hear the words WAF, or write amplification factor, quite a few times in this presentation. And write amplification factor is actually the most important thing to understand about SSDs. The way that NAND writes is in programs in pages. Typically a page size is 16 kilobytes, but it erases in blocks, which are generally hundreds or thousands of pages. And these are today somewhere between 50 and 100 megabytes in these block size, erase block size. So the fact that you have to erase the blocks before you write it in NAND in programming causes this thing called write amplification or garbage collection. So when the drive is full and you go to write data and there's already data there, the SSD has to do garbage collection, move that data to free space or over provisioning to go write the new data. So one of the holy grails of SSDs is seeing if you can reduce write amplification factor. And one of the key strategies to reduce WAF so far has been to over provision the drive. You've heard of like 3 drive write per day drives. This is generally just over provisioning and giving it more free space to the drive to allow the drive to have better garbage collection efficiency. But flexible data placement is a feature that is designed in NVMe Express, and especially really driven by hyperscalers to basically intelligently place the data on the flash that's consistent with how an SSD controller actually works in erase blocks and NAND channels and striped across super blocks, which is how SSDs have very fast performance. So this improved isolation leads to better quality of service, but the reduction in WAF, you get all the benefits. You get better performance, better capacity utilization, better endurance, and lower over provisioning leads to lower total cost of ownership, basically due to this higher device utilization. We've heard about how FTP can reduce WAF, so this directly improves performance, improves the endurance. You can reduce the amount of over provisioning you need. One of the things that's very common in a hyperscaler might take a 2 terabyte drive and reduce the capacity to 1 terabyte usable, up to 50% over provisioning in a database application like RocksDB or something that has a lot of writes. And so if you can use the full capacity of the device, that allows for reduced over provisioning and improved TCO. The other thing that's really interesting, if you reduce the WAF, you also improve the quality of service because you're doing some isolation for the specific workloads and the data that goes with the NAND. The key topic of this talk is about the seamless integration, the backwards compatibility of flexible data placement. There has been features like zone namespaces and streams in NVMe Express before, but these were not backwards compatible. These required pretty significant software development changes to take advantage of them. So the scalability advantage of FTP allows you to actually scale the capacity without having to over provision the drive. And again, this all leads to lower total cost of ownership. Whenever you get all 3 benefits with lower WAF. You get better performance, better endurance, better capacity utilization, and then better quality of service, and this leads to lower total cost of ownership. One of the customer use cases for FTP, again, FTP was developed in NVMe Express, and Google and Meta were 2 of the hyperscalers that helped develop the specification with multiple SSD vendors also. But it was really about these multi-tenant, multiple namespaces, multiple applications, multiple VMs, containers, microservices, log structure, DBs, caching. And so there's a presentation at OCP that the Meta and other folks Google went through kind of some of their workloads, but there's support for FTP and what's called CacheLib. This is one of the most popular caching libraries that is used in I think over 80 or 90 production applications at Meta. It's a very popular caching application, so now it has native support for flexible data placement, which can reduce the WAF significantly, and again, improve the performance and give more of that space to the applications for caching. And again, these log structure workloads like RocksDB, this is really important to reduce the WAF. And again, these are one of the applications that, again, hyperscalers are highly over provisioning today, so FTP can really help improve the capacity utilization of these workloads. When we look at just the sheer number of cores, Intel has Sierra Forest right now that is 144 cores, and they've announced Clearwater Forest, I believe, that has double that in 2026, and the average capacity is needing to grow to basically of the compute SSDs to match these VM performance. Again, if you're in a compute workload, you generally have a certain amount of like SSD capacity for each number of cores in a VM. Like a typical VM that's running a web server or a database or something just needs a little bit of capacity for every 4 cores or 8 cores. So it's not surprising that when we see this core count growth for CPUs, that we're also seeing the compute SSD capacity, average capacity, grow over time. And so this is a really important use case for FTP, because when the drives get bigger, you're putting more workloads on them, and the workloads start to look more mixed and more random, and you start to have this noisy neighbor problem where one workload doing one thing is impacting the quality of service and performance in another workload. This is an example of a workload we're giving where you're just taking a drive. Normal drive means FTP off, and then FTP on means FTP on, and we're basically just running a 50-50 FIO workload with mixed sequential workload performance. And FTP on versus FTP off, we're able to improve the mixed workload bandwidth by 85%. So again, this is one of the things when you can reduce the WAF, and in this mixed sequential mixed workload performance, you're able to significantly improve the mixed workload performance. So we mentioned some of the FTP use cases are cloud native environments, anything that has multi-tenant containerized workloads, anything that's doing a lot of things to one drive at the same time is going to help reduce that impact of garbage collection. Cache-lib, again, as mentioned, is one of the really important caching applications that FTP can help. Anything that's a mixed workload, certainly like a write-intensive workload, if there's lots of write streams, or if there's random writes in some places of the drive and sequential writes in the other, these are really places where FTP can help. So what we're going to talk about for the rest of the presentation is multiple namespaces. So one of the reasons today you can have multiple namespaces is basically to just make it easier for the operating system to see different little namespaces, and you can give those to different applications, or physically provision them with different settings. But FTP allows you to do something really interesting, which is basically in FTP there's this thing called an RUH, or reclaim unit handle, which you can actually tag a specific namespace with one of those reclaim unit handles and make it so all the writes that go to that namespace are tagged with that data. And so if you have different applications running in different namespaces, you can get basically all the benefits, or most of the benefits, of FTP without actually having to do any software development. So this simplified management allows you to basically split up, say for instance, an 8 terabyte drive into 8 1 terabyte drives, give those to 8 different applications, and then all of a sudden now you have much better WAF and mixed workload performance. And the other benefit of this is that they're all physically on the same drive, so when one of the VMs are idle, you can share that bandwidth and performance with the other namespaces. Where if these were on physical separate drives, you can't do that. So this is where I first got my idea for this experiment. We have basically an FIO script that does 8 different sequential write streams. 2 of them were 128 kilobyte in block size, 2 of them were 64K, 2 of them were 16 kilobytes, and then 2 of them were 4K. And they're all sequentially writing to the drive at the same time. So from the drive standpoint, this starts to look a little bit random. Even though these are sequential write streams, they're different block sizes, and they're coming in at different velocities and different megabytes per second, and they are coming from different streams and different threads doing through FIO. So in this workload, when we just turn on FTP and tag each one of these write streams with its own RUH, we're able to basically reduce the WAF. You can see this red line down to the blue line, which is you have a WAF of 2 to 3 over here, and it's getting reduced to 1. Well, the bandwidth also goes up proportionally too. So this is, it's getting, say, 1,500 megabytes a second. We're able to go all the way back up to like 5,000 megabytes a second just by turning on FTP. So I had an idea. I said, what if you didn't have to actually tag the applications with the FTP RUH? What if you actually just took those workloads and just split them up into different namespaces? Would you get the same results? And so this was the genesis of this experiment I was going to be performing. So if you guys are not familiar with Proxmox virtual environment, it is a virtualization platform similar to something like VMware, but it is open source. They also provide like an enterprise model like Red Hat for support. But I'm just running this on a little desktop at home. I'm redoing this experiment at a much larger scale now with a PCIe Gen 5 server. But one of the key things is with FTP, you can take this, again, I have this 8 terabyte or 7.68 terabyte drive, and I'm splitting it up into a bunch of different namespaces, and you can see here the namespace size is 940 gigabytes. And what I'm going to show you is I have two experiments. Obviously the control, I have to basically take one namespace, and I'm going to make a bunch of different, in Proxmox, the way that you usually split up a drive is to format it with an LVM, or logical volume management, and then give each of those VMs a certain provision LVM space. And so that's very, very typical to how you provision one single storage device into, and typically you want data protection. Like if you're doing this in a production system, you'd want to use that. They love ZFS. It's kind of built into Proxmox, or LVM. You can do like, different RAID levels, like RAID 1 on top of that. They also support Ceph. But in this, if you guys want to follow along, I have, kind of released all my scripts on GitHub for the Ansible playbook of how I actually did this test. But the idea was basically in the control to have one namespace with one big logical volume management, and give each of these 8 VMs. So I have node test 1, test 2, test 3. These are 8 virtual machines. Each one of them have, a little bit of DRAM, a few cores. These are not like super high power beefy VMs, just enough to run FIO. But they get a drive, and now in the control version, they get basically just a logical volume that was attached from the one single namespace. And then in the experiment, the one I'm going to be changing, I'm going to actually split up the drive in multiple namespaces and give each VM its own namespace with its own LVM. So the first experiment I did was basically in the control version, when I had, where I had just one namespace, I just said, let's take 8 VMs and write 128 kilobytes sequentially to each VM. And this was surprising. I got, over 6.5 gigabytes a second of bandwidth. You can see here is kind of, you can see the average queue size was extremely high, like thousands, 4,000 queue depth, because I'm running FIO, basically running it to 8 VMs and running a huge workload. But it was kind of surprising. This actually resulted in a WAF of 1, even with 8 write streams. So we did some digging, and this is actually a little bit interesting, is when you have lots of write streams and they're all the same size and they're all very high velocity, like they're all being written to very fast, and the turnover is very fast on the NAND. This actually resulted in a kind of low WAF, which was surprising to me. So again, this is kind of fun. I learned something new during this experiment. Now this is not going to be the case in all real workloads. Are not so nice and neat. So we need to find a way to measure write amplification factor. So one way we can do that is to use the OCP C0 log page. This drive supports it, which basically has this thing called physical media units written, which tells you exactly how much raw writes to the NAND that have happened. And then you can use the smart for host writes, data units written, which is great. And then you just basically record this data before, and this is kind of showing you what my script looks like to do this. You record the data before, run the workload, record the data after, take the delta, what was the change in host writes, what was the change in NAND writes, and then the WAF is basically that delta change in NAND writes over host writes, and then you have the write amplification factor. Now this is much actually easier to do with FTP enabled, because there's just one command that does it. You can just say nvme FTP stats, and you give it an endurance group 1, and you can just say it says host bytes and media writes, and the way to calculate WAF is just the NAND writes over host writes. So very, very easy. So this was the control I mentioned. I created a single namespace. You format it with logical volume management. Give this 940 gigabyte with virt.io to each one of these Proxmox VMs, and they show up as /dev/vdb in each of the hosts. In each of the virtual machines, I had run an Ansible playbook that basically collects the smart data that I just showed you, kicks off FIO on all these VMs, because we need to start the FIO. We need to actually make sure it started correctly. And then we let it run for a certain amount of time, and I believe this ran for like 5 or 6 hours here in the scripts. And then we're going to collect the smart again and then parse the output. And then this output, my little script, basically shows you the megabytes per second. I just mixed in some 4K reads into the write workload, and then split the writes into 4K, 16K, 64, and 128, just to kind of see what would happen if we mix some reads and writes together. And this was what happened with the control. So I had a WAF of 1.7, write bandwidth of 2.2 gigabytes a second, read IOPS of 44,000. And so now we kind of have a baseline, which is similar to what we saw before, which, hey, you mix some workloads together, you're going to get a WAF that's not 1. So how do we turn on FTP? This is really important. So I wrote a blog post And if you want to follow along on the blog post, this will give you lots of information on this presentation I just described. But it's very easy. So first thing you have to do is just delete the namespaces. So this first line is basically just saying, okay, if there's a bunch of namespaces on this device, delete them all. And then we're going to basically enable FTP. So this NVMe set features /dev/NVMe0. This is the command to enable FTP. We're saying, please enable FTP. Now, if you try to do this before you've deleted the namespaces, it will fail, because in the FTP spec, it says that you have to remove the namespaces first. So again, it's very, very important that you follow these steps exactly, or else it will not work. Now, again, you want to look at the FTP config, which basically tells you, hey, this is the RUH status of the drive. Here's how many placement groups there are and placement handles and all that stuff. The config will tell you what the drive supports. And then this script I basically said for 0 and 7, we're going to be basically create a new namespace. Each of these namespaces is going to be 940 gigabytes. And then we're going to attach and tag it to a certain placement handle. So each one of these is going to have one placement handle. And after you're done, I'm going to attach the namespaces back to the controller. And when I do an NVMe list, you can see now I have a bunch of namespaces. NVMe 1, controller 1, namespace 1, controller 1, namespace 2, controller 1, namespace 3. You'll see I have 8 namespaces of 940 gigabytes. Now, if you were astute, you might know that a 7.68 terabyte drive divided by 8 is 960 gigabytes. So the 940 has to do with some of the RUH size. I mentioned with some of that actual physical mapping of how big the NAND blocks are. So we enabled FTP and we ran the scripts again, and this is my Grafana dashboard. I know you won't be able to see much here, but you know the red is the I/O weight. This is kind of the CPU utilization and disk IOPS and queue size. But you can see these workloads that were some of the larger block sizes, the 128K, we're writing at a peak of 1.7 gigabytes a second on this. So we already know it's going to be faster than the one before, and it indeed is. So with FTP, we run the exact same playbook, and it works. The WAF went from 1.7 down to 1. And this is one of the, I don't know, again, I mentioned when I gave this presentation live, why did I put 4K random read into mixing it with the writes? There wasn't really any really big reason besides, I was just messing around, and this was a kind of a fun experiment. But you can see, surprisingly, this background random reads went up quite a bit, 182%. The write bandwidth increased by 150%, so it went by from 2.2 gigabytes a second to 5.5 gigabytes a second, and the total bandwidth on the drive is over 6 gigabytes a second. And the endurance, again, if you take the WAF from 1.7 down to 1, then your endurance increases by 170%, or 1.7x. So this is just absolutely massive. So the key output and key learnings of this experiment were we actually don't even need the VMs to be aware that FTP is even turned on at all, because we can do it at the namespace level. We can turn on FTP on the namespaces and then give these to virtual machines, and then the virtual machines can just use them normally, and they don't even know that FTP is enabled. But underneath on the NVMe driver knows that this namespace is associated with this RUH, and all the data written to that namespace will get tagged with those reclaim unit handles. So this was just a very, very fun experiment. I am doing a more involved version of this experiment now that I've kind of done this baseline and kind of understand a little bit how it works. This was a lot of fun, and we're going to be kind of following up on this at the OCP Global Summit. So with that, hopefully you guys learned a little bit about FTP, and thank you. Bye-bye.